right, so I'll take a look at these problems. Okay, so you predicted, which atom did you predict would be basic or nucleophilic?
The oxygen with the negative charge.
Good. What about the left-hand oxygen? That has a lone pair, so is that going to be nucleophilic?
No, it won't actually. It has a hidden positive charge, so it wouldn't be nucleophilic.
Right, good. Okay, good. So that's a good answer for that problem. Let's take a look at the next. All right, this one's a little tricky actually, but I think you gave a good answer. How many charges should we change in every new resonance structure?
Oh, yeah, I missed that positive charge on the nitrogen. We should change to...
All right, and that's very important. So now what reactivity would you predict?
Oh, yeah, that's funny. I didn't really think that one through very well. The carbon 1 in either scenario should be an electrophile. Because either in the first resonance structure it has a positive charge, which would make it an electrophile, or in the next resonance structure it's attached to an atom with a positive charge, which would make it a good electrophile.
Okay, so that new analysis is a good one. That's a good explanation of the new analysis. Okay, so that's an important one to mark. I think that was probably just a careless mistake, but our goal here is to get to the point where these are easy enough that we almost never make those careless mistakes either. Okay,
Yeah.
1 second. All right, so let's go ahead and take a look at the next picture. Let's see. Okay, all right, so the next one we got correct, and we did a good job predicting the reactivity.
Okay.
We had some new reactivity we wouldn't have predicted. You wouldn't have predicted that the oxygen would be nucleophilic from the left-hand structure, because neutral atoms can't be nucleophiles without hydrogens. So there was new reactivity from the right-hand structure. All right, let me take a look at the next. Okay, that's good for this next example. That's good for the next example, the right structures and the right reactivity. Probably you could have made your life a little bit easier here. Let's try this one alternative way. Let's try this again. Maybe off to the side, draw the first molecule again.
Let's see.
Good.
Did I remember that right?
Okay, yeah, that's good. Good. Now, this time try drawing a resonance structure using only one arrow.
Okay. Could just do that.
Good. And now let's draw the picture we get from that.
like that.
Okay, excellent. Very good. So you got the same exact resonance structures as before, just in a different order.
Yeah,
But this
that
is
doesn't.
maybe a slightly better method because it doesn't require you to kind of reverse the order of the arrows and go back to one that you'd skipped before. So
Okay.
there's nothing wrong with the way you did it before. What you did before would certainly be correct, but this is maybe a better approach. So the point is, if you're trying to draw all the resonance structures, you do that by drawing the fewest possible arrows at each step. If you're trying to draw all the resonance structures, you draw the fewest possible arrows in each step, so that you don't skip a structure and then have to go backwards towards it, so to speak.
Okay.
Now, oftentimes in organic chemistry, you're not trying to draw all the resonance structures. Sometimes in organic chemistry, you're just trying to get to a particular resonance structure, and then it can help to draw multiple arrows. It depends on what your goal is. Okay, so anyway, I just wanted to show you this alternative. Let's scroll back to the left. Like I said, what you did on the left was also okay. What you did on the left would have been best if, say, you were mainly interested in how carbon-4 could react. If you were mainly interested in how carbon-4 could react, it would make sense to go straight to that resonance structure and skip over the one where the positive charge is on 2. So if your goal was to see mainly how carbon-4 could react, it would make sense to draw the 2 arrows at the beginning like you did here. But if you're trying to draw all the resonance structures, it's probably a little better to draw just 1 arrow at a time here, so that we don't end up skipping carbon-2 with the positive charge and going back to it. Okay, like I said, what you did was right here. I just thought the other way might be a better approach. Okay, so let's take a look at the next example.
Okay, thanks.
All right, check your work for this next example.
Oh, I did that again. You had warned me about that, and I still lost it a little bit. So that would make it so oxygen, because of that hidden positive, would not really react as a base.
That's right. We can be confident. That's right. That actually really does change the reactivity. You're never going to see this oxygen act like a base. No way. So that is important for us to have seen here. Okay, yeah, so that made a difference. You said I had warned you about it. What particularly were you thinking of that I warned you about?
Oh, just that a neutral atom that's donating electrons is often forgotten to be left with a positive charge.
Exactly. Okay, well, you did forget to apply that here, but it's good that you remembered that general rule, because that is quite important. So yeah, you can see that does happen. You can see why that happens. You're probably not going to change. You're probably not going to forget to change the charge on 2. You're not going to forget to change the charge on 2 because it jumps out at you that it started with the charge, so your attention was already drawn to it. But it's easy to forget to change the charge on a neutral atom because it doesn't seem like it needs it so much because it didn't start with the charge. All right, so how many charges do we change for every new resonance structure?
Could change 2 charges.
The best thing to do is just force yourself to ask yourself on every single resonance structure, which 2 charges did I change? 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 That should just be part of your habits. Remember, we also saw that applies to reactions as well. After every step of every mechanism, and after drawing every new resonance structure, you just need to be in the habit of checking which 2 charges did I change. Because notice sometimes the molecule doesn't kind of remind you to change a charge. This oxygen doesn't look like its charge needed to be changed, but it did. Okay, and that's not a small issue, because what's the most important factor in organic chemistry?
The charges.
The charges. That's the main reason we're doing the resonance in the first place. The whole reason we're doing the resonance is to see whether there's any interesting alternative charges. And here there was. If you just looked at the first picture, you might have possibly thought the oxygen would be basic, but not. Well, actually, that's not true. It was the new picture with the wrong charge that you thought was basic. But now the new picture you can see is not going to be basic either. Okay. Let's see. Okay, so now I think we have the correct reactivity. We made that mistake here in a couple of these, so maybe from now on, as we're going through these, I'd like you just to double check each one as you look at it on your own, making sure you change 2 charges on each of them, rather than me prompting you for that. So I'll go ahead now and take a look at the next example. Okay. All right, that's very good on the next example. But notice here that, again, you ended up kind of having to reverse yourself and go backwards to pick up a missing resonance structure, if you see what I'm saying. So
Yeah.
just for practice, let's draw maybe what might be a better approach here using just one arrow at a time. Like I said, what you did wasn't wrong, but I think it's better. Another approach might be more reliable. So let's draw it the alternative way where we only draw one arrow at a time.
Okay. Yeah, that does seem more complete, more thorough. You're not as likely to miss a resonance structure by doing that.
And it'll be especially helpful if there's maybe 4 or 5 resonance structures. If there's 4 or 5 resonance structures, to get all of them, it's helpful to just get them kind of in order rather than skipping over some of them and having to go backwards. Okay. All right, so that's a slightly better approach. So if you're trying to draw all the resonance structures, the way to do that is to draw the fewest number of possible arrows at each step. Let's scroll back to the left.
And I think that even fits the rules that we had better.
That's true. That's true. Although it is good to see that these resonance structures are reasonable. So actually, it's good to see that if you draw multiple arrows, you can have situations that break those rules. So there's nothing wrong with seeing these arrows. What I was going to say was, if you're mainly interested in how carbon-3 is going to react, then the way you drew it is just fine. If you're mainly interested in carbon-3's reactivity, then it's just fine to draw the 2 arrows and go directly to the positive charge on carbon-3, and maybe even just leave the last one out. So very often in organic chemistry, we will draw multiple arrows so that we can focus on the particular resonance structure we're interested in. But for this particular exercise, our goal was to draw all the resonance structures, and for that, it's better to draw fewer at a time. Okay. Okay. So, like I say, what you did certainly isn't wrong, but it's good to maybe when you're trying to draw all the resonance structures, the way we did it off to the right is probably a more reliable approach. Okay. In any case, you did get that right. So I'll take a look at the next one.
Okay.
Okay. Yeah. We need to.
Oh, there we go.
Great. Okay. Good. So that's the right reactivity. And those are the right resonance structures. Now, this is a case where you have to reverse the arrows. First, you had arrows pointing to the right, and then to get the other resonance structure, you had to draw arrows pointing to the left. And if you wanted to do it in one step, you had to do 3 arrows at a time, which is fine. So you did that correctly. This is a case where we did discover new reactivity. Based on the first picture, we would not have predicted the oxygens to be nucleophilic. That was revealed in the new structures. Okay. Okay, good. So let's scroll down. Okay, that looks good. So the new structure revealed a new reactivity. We wouldn't have predicted the nitrogen to be nucleophilic without that new structure. And that's a good way to draw the resonance structures there. That's correct. Okay, so let's continue.
think there's a resonance structure that I missed on this one.
Okay, go ahead. So go ahead and try drawing that.
And I think it would actually make these arrows make a little more sense.
You got very proficient with that cut and paste operation. That's good. That's handy.
It does help, yeah.
Too bad you can't do that on a piece of paper.
I know, that would be great. So, yeah, I think if I were to just move one arrow, just use one arrow there. Oh. And it seems that carbon 2 and carbon 3 both or not 3, I meant carbon 5 could be electrophiles.
Okay, that's good that you saw that. So this is another case where we could find more resonance structures if we draw fewer arrows at a time. You would use 2 arrows, but there was a way to use only 1 here. Sometimes you need 2 arrows, but here we didn't. So we ended up missing a resonance structure. Now, actually, that resonance structure, well, I don't know if that was really necessary in a sense. Well, I don't know how much extra information that gave us. Take a look at your very first picture that you started with. What reactivity would we predict for carbon 5 in the very first picture?
I don't know that I would. I guess you could have a delta positive charge on it, making it electrophilic.
Okay, that's right. The only problem was the "I guess" part. So yeah, we definitely it definitely would be electrophilic even from that picture. So I think that's one thing we're still having a little bit of trouble with is seeing the delta positives. I think you're definitely seeing the full positive formal charges when they occur, but I think we're having some trouble applying the delta positive approach. But that is important as well because many molecules don't have formal charges. So if there's no formal charges, we should definitely look for delta charges. That would be a good thing to put in your notes. Remember, you don't use delta charges when a molecule has formal charges. You don't use delta charges when a molecule has formal charges. But if the molecule has no formal charges, then we should pretty much always look for delta charges. I think that's something we're not quite in the habit of doing yet. So that's an important thing to emphasize in your notes. So we didn't, in a sense, the middle resonance structure doesn't add any new information because we could already have predicted carbon 5 to be electrophilic. The surprising thing is that carbon 2 is electrophilic. That's what we needed the resonance for. But anyway, if you're trying to draw all the resonance structures, then that middle resonance structure is one to draw too. So these are all 3 of them. So like I said, if you were mainly interested in carbon 2, you might have just done it the way that you did it before and just used the 2 arrows to put the positive charge on carbon 2. But if we're trying to draw all the resonance structures like we are here, then this approach is better. All right, and again, we saw it's important to be more in the habit of looking for those delta positives. Let's go back to my screen for a second. So I just wanted to remind you of this handout. Remember that when you're looking for electrophiles, first you look for positive formal charge, but if there are no formal charges, what do you look for next for an electrophile?
The delta positive charge.
That's right. As I said, I think that's something that we haven't been quite doing enough, seeing those. So when do you look for delta charges when there's no formal charges in the molecule. If there's no formal charges in the molecule, we should kind of automatically look for lone pairs or delta charges.
Yeah.
If there's no formal charges, the next step is to look for lone pairs, carbon-carbon pi bonds, and delta charges. That's something, especially the delta charges, we're having a little trouble seeing. Okay, so let's go back to your screen. Let's see. All right, I'll look at the next example.
Okay.
So this was another case where we had a neutral atom at the beginning of the arrows, and this time it looks like you remembered to change the charge to positive. We had a little issue with that on some of the earlier examples, but that looks correct.
Good.
And the reactivity is correct. The resonance structure here gave us some new reactivity. We wouldn't have predicted the oxygen to be acidic from the first picture, but the second picture shows how it can be acidic. All right. So let's take a look at the next example. Okay, good. All right, now this one's a little tricky. Do you remember what the name of this functional group is here with the N and the two oxygens?
It is a nitro group.
Yeah, a nitro group. We talked about how that's kind of a special case last time. So
Yeah.
what pattern did you obey here? Well, you use the pattern of a lone pair on an atom that's attached to an atom with a pi bond. So that's good. That's a good resonance structure. However, there was a whole special pattern just for nitro groups that I think you forgot to apply here.
I did.
Yeah.
Yeah.
So let's try to apply that now as well.
Funny, I had started drawing this out, and then I thought, oh, that's too many charges, but I had forgotten about the exception with nitro groups, that they can actually have more charges in the resonance structures. So this would actually reveal that carbon-1 is electrophilic. Whereas before it almost would seem that it's nucleophilic.
Yeah, so that's a big deal. The whole point of this, yes. So the nitro group has completely changed the reactivity of that alkene carbon-carbon double bond. I was mentioning that nitro groups are an important functional group in the second semester, and you can see why, because they completely changed the reactivity here of the functional group. We didn't draw that third resonance structure correctly. Check your work there.
Oh, I didn't write that pi bond, sorry.
Okay, that's important too. Although notice, even though that's important, the most important thing is that you got the charges right. Even though you left that out, you were still able to pick the reactivity right because you got the charges right. So the charges are even more important than the bonds, although ideally we want to get both of them right. Okay.
Yeah.
Okay. So this is an important example here. We didn't do too many nitro examples last time, but anyway, you can see why that we need to think of nitro as a special group, because it does completely change the reactivity here. Without the nitro group, we would expect the carbon-carbon pi bond to be nucleophilic. So with the nitro group, it turns carbon-1 into an electrophile. And actually, I can see why you would say the two oxygens could be nucleophilic or basic, but I can't think of any reactions in OChem where they actually act that way. So generally in OChem, the nitro group is going to change the reactivity of the other parts of the molecule. So what you wrote down is perfectly logical. It seems to make sense. But there's no, generally in OChem, we're not going to study any reactions where the nitro group itself reacts. Instead, we're always going to study reactions where the nitro changes the other parts of the molecule. So I wouldn't necessarily call that a mistake, but there probably are reactions where the nitro group would react, but you're not going to see those in your class. The point of the nitro group is to see how it changes the other parts of the molecule. Okay. All right. So notice that normally we would be very suspicious of this because there's 4 charges. We don't usually we don't even want to have 3 charges. Usually we don't even have 3 charges. So I can see how this would feel wrong to you. But that's why we just had to learn it as a specific exception. With nitro groups, 3 or 4 charges are okay. We didn't really quite explain why that is. We're just memorizing that. With nitro groups, 3 or 4 charges are okay. Let's see. Okay, so yeah, it looks like we did get that one incorrect because the most important resonance structure we hadn't drawn yet. Okay.
Yeah.
All right, so we'll take a look at the next example. Okay, here I was trying to trick you, but you saw there was no resonance. Good, because the pi bond is too far away from the positive charge. Good. You might possibly get a reaction here. You might possibly get some kind of reaction between carbon 1 or 2 and the carbon 4, but it would be forming a sigma bond, so that would be a reaction. Or, well, not here, because that would probably leave, well, I don't know, maybe. All right, yeah, you might possibly get some kind of reaction between 1 and 4, but that would not be resonance. Okay? All right, so it looks like you didn't fall for any of my clever, devious traps here. So, yeah, the next one, there was no resonance either. Good. The lone pair is too far from the pi bond. This next one I thought was tricky, but there's really no kind of driving force to move any of those pi bonds in that third example. So there are no resonance structures there either. That's good.
Yeah.
You didn't fall for the next one. I was trying to trick you into having the negative charge form a double bond with the nitrogen, but you remember that nitrogens have complete octets, even when they have a positive charge. So there's no resonance there. There's no good resonance structures for that next example. So those all look good. None for the next one. It looks like you didn't quite write down an answer for the last one. That's right, ditto. Okay. All right. So I probably should have mixed those in with the rest of the examples to make that more challenging, but I was too lazy to do that. But anyway, you stuck to your guns and you saw that they were all no resonance. So that's important too. It's just as important to know when there isn't resonance as to know when there is resonance. So it's good that you got all of those correct. Let's see.
So I had a question. That the alkene with the alternating pi bonds.
Yes.
That one was throwing me off a little bit because I was remembering conjugation, and that I don't remember it well enough to be able to relate it with resonance, compare it really. But I realized there is no pull for those electrons to be moving, and so that's why there is no resonance.
Right.
But it would be conjugated, right? Is that...
Okay, that's good. That's an excellent point. That's good that you were thinking about that. Yes. So conjugated means alternating single and double bonds.
Okay.
The molecule is conjugated if it has alternating single and double bonds.
Okay.
That's one definition anyway. And this molecule does have alternating single and double bonds. So it's true, it is conjugated. But conjugated molecules don't necessarily have resonance.
Okay.
So that's a good point. Conjugated molecules tend to be more stable than non-conjugated. So this molecule would be more stable than we might expect, but not precisely for resonance reasons. By the way, I'm a little surprised you mentioned that because usually conjugation isn't studied in the first semester. Your class covered conjugation in the first semester?
It seems like we touched on it briefly in talking about like the wavelength of light that it typically absorbs. And I think that...
Okay, maybe you were going over ultraviolet visible spectroscopy. That is ultraviolet visible spectroscopy is used for conjugated molecules.
Okay.
Although even that is usually a second semester topic. But, all right, but now I can see why... so you're saying you went over it for spectroscopy?
Probably.
Perhaps. Okay. Well, anyway, there's nothing wrong with knowing it, even if you're a semester ahead. So that's good. All right. So yes, conjugated molecules are usually one of the key topics early in the second semester. I don't know if you remember, but usually at the end of the first semester, you study alkenes, carbon-carbon double bonds, and then at the beginning of the second semester, you study conjugated alkenes. That's probably a topic you would get into early at the beginning of the next semester, although maybe your class did it in a slightly different order. Okay, but anyway, that's a good point. So yeah, that molecule is conjugated, but that doesn't mean it has resonance.
Okay.
Okay, good. All right, let's see here. Okay, overall, that's good work on those problems. For the most part, you were doing a very good job at finding the resonance arrows. I think most people have find that to be difficult, but you never didn't seem to find that to be too difficult, so that's good. There were a few mistakes where we didn't change the two charges, so that's something to watch out for. Go back to my screen. Let's try this example. Try this on your screen. Try drawing resonance for this example.
Okay.
We want to try to draw all the resonance structures.
All right. Okay, so that's all of the resonance structures.
Excellent. So now let's predict the reactivity.
Okay, I think as far as we're concerned, we're mainly looking at carbon-2 as being an electrophile.
Perfect. Okay, that's a good answer. So theoretically, you would expect both oxygens also to be nucleophilic or basic, but you're not going to study reactions where that actually happens in your course. So we may as well focus on what's going to happen in the course, which is that carbon-2 will be electrophilic, which is not what you would have predicted at all without the resonance. Good. Now, the way you drew this is excellent for what I asked you to do. What I asked you to do was draw all the resonance structures. So the way you did this was good. But notice that if all you really cared about was reactivity, we might as well just skip the second resonance structure because it doesn't change the reactivity. So generally in OChem, when you're generally with OChem for nitro groups, you don't bother flipping the negative charge from one oxygen to the other. You just go straight to the resonance structure where the positive charge is on the rest of the molecule, because that's the only thing that's going to change the reactivity. But since I asked you to draw all the resonance structures, what you did was correct. So what you did was correct. Later in OChem, when your goal is just to predict reactivity rather than draw the resonance structures for the heck of it, then you're going to be maybe just going to the third resonance structure. Okay, so anyway, you did that correctly. I just wanted to review this since there was an example in the homework where we missed the key resonance structure for the nitro group. Remember, there was a couple of new things we had to learn here. Oh, one moment. Okay, so in this case, so previously you messed up the nitro group and here I did. Do you know how many bonds does a neutral nitrogen usually form? How many bonds does a neutral nitrogen usually form?
Yeah, it should have a positive charge on that nitrogen.
Yeah, that was my fault because I didn't put that in the first place. So let's go back and put in the positive charge in the first picture.
That makes more sense. I didn't pick up on that.
All right, yeah. Okay, so I left that out. All right, so what I was going to say here is, what was I going to say?
They normally have 3 bonds, right? A nitrogen.
Yeah, that's right. Something else that's worth noticing is you might have predicted that from our previous rules, you might have predicted that carbon-1 would be electrophilic based on the second and first resonance structures because it's attached to an atom with a positive charge. You couldn't do that before because I left out the positive charge. But actually, that's not how the reactions that you're going to study in the course actually work. The reactions in the course are generally going to focus on the carbon-2 position that has a full positive charge with an incomplete octet in one resonance structure. So we can leave that out of the reactivity as well. So nitro groups, in some ways, are some of the exceptions to the rules we've seen before. So one thing I wanted to mention here is we ended up with a picture with 4 charges, but we know that's okay for nitro. And also we used kind of a new pattern. In the second picture, that didn't really, those arrows don't really fit any of the other 5 patterns for resonance. So it's just a new pattern when you have a pi bond on an atom that's connected to a nitro group. That's just a new pattern for resonance. Okay.
Okay.
All right, so I'll go back to my screen. Oops. Should fix this. One thing that's useful to draw here then. So actually, usually in organic chemistry, nitro groups will be drawn like this. That is, they're not usually going to draw the Lewis structure for you. They're just going to be drawn like this, and they don't bother showing the formal charges either. Usually in organic chemistry, formal charges would be drawn for you, but this is an exception. They don't usually draw the formal charges, maybe because there's 2 of them and they balance out to be neutral. So it's good to memorize that this is the Lewis structure for a nitro group, because that Lewis structure is not obvious from looking at this. Notice that if they just drew this picture, it wouldn't be obvious at all that carbon-2 is electrophilic unless you draw the Lewis structure and you draw the new resonance structure. So that's something to keep in mind. When you see a nitro, it can help to draw the Lewis structure so you can see the extra resonance, which you might not, otherwise you wouldn't normally see. Okay. Let's see here. Yeah, if you don't draw the Lewis structure, you don't even realize there's another resonance structure here. Oh, here's the point I wanted to make. Does this nitrogen have any lone pairs?
Yeah.
So what role would we expect it to play?
It could play the role of nucleophile, or even a weak base, it looks like.
That's a good answer. That's good that you remembered the base as well. Does this nitrogen have any lone pairs?
No.
So would it be a nucleophile?
Nope.
And would it be a base?
Nope.
But notice, you wouldn't know that if you didn't have this Lewis structure memorized. This looks pretty similar. They look quite similar. Normally, we assume there's lone pairs on neutral nitrogens. This looks neutral, even though it isn't. So that's what I wanted to say.
Yeah,
you have to remember that nitro groups behave differently than they might seem. This nitrogen is quite different from this one. It has no lone pairs. In fact, it has a positive formal charge. So that's worth memorizing, because usually the Lewis structure won't be drawn for you with the nitro group. You need to have that in your mind. Okay, so that's something I wanted to point out. All right. The first semester doesn't focus much on the chemistry of nitrogens, but that's focused on a lot more in the second semester. So those are some issues there.